In this course, we've been asking, how do you describe a test in a way that lets people know whether they can trust its answers, in a way so they can know what % of the time are its answers correct? If you ask them, traffic police will answer that question. Their answer is wrong. It misleads juries and judges. You've arrived at the first of the 2 key lessons in this course. If you don't want to do the whole course, it's okay to do just this video and the next one. But get ready, this one is the longestest and the hardestest. You're going to learn how police and prosecutors describe the performance of their sobriety tests and why the way they do that wildly overstates the test's validity. The basic idea in this lesson is pretty easy enough to explain with pictures. The math is hard. We'll start with the pictures. I'll show you the math, and we'll wrap up with more pictures. If you're an attorney, you don't need to be able to do the math yourself, but you should know it. You should know it's there, and it would be good if you knew it well enough to direct and recross your expert as they explain what NHTSA's validation studies actually reveal about the terrible scientific accuracy of traffic police sobriety tests. If you are the expert, it will help your usefulness to juries and judges to know the math well enough at least to apply its results to traffic police sobriety tests as explained in this and the next video. As usual, I'm likely someday to redo this video, and when I do, the video you're watching now will disappear and it'll get replaced. So if you want a link, don't link to the video, link to the channel. Let's think about what's going on. Before traffic police arrest someone for impaired driving, they do a traffic police sobriety test. But that's not all they do. The process starts when they observe the flow of traffic and pick out a car to stop. Police call that phase 1 of their investigation. Their training manual devotes a long chapter to just that subject, special techniques to spot impaired drivers. Next, the officer walks up to the window and talks to the driver. Phase 2, personal contact, another long chapter, more specialized techniques. Some drivers pass phase 1 and phase 2. The officer doesn't think they're drunk or high. He sends them on their way without alcohol testing. Other drivers fail phases 1 and 2, and the officer takes them on to phase 3. Police call this pre-arrest screening. Only now, in the last of the 3 phases, does the officer do the SFST. NHTSA and the IACP, the National Highway Traffic Safety Administration, and the International Association of Chiefs of Police, they lump all those phases together into one thing that they call the DWI detection process. Remember the title of police DUI training? It's the DWI detection and SFST course. The SFST doesn't get going until Chapter 8, page 283 in the current instructor's manual. The SFST is just one element of the larger DWI detection process. So the way police see it is the officer does the 3-phase process and considers all the factors and then makes his decision to arrest or not. And when they check to see whether arrested drivers actually had a high BAC, it turns out the officer's decisions to arrest were correct 91% of the time. That number comes from the San Diego SFST study. Other studies show about the same. In SFST validation studies, the people police arrest for DWI, they do have a high BAC. So we're done here, right? Nope. No, we're not, because now things go south. Here's how NHTSA and prosecutors and police think about this process. They end up attributing the 91% to the sobriety test, to the SFST. They say officers using the SFST were 91% accurate. The idea is that later, in your impaired driving trials, when your defendant's officer used the SFST, his answers will also be 91% correct. After all, the science shows that officers using the SFST are correct 91% of the time. But the sobriety test was only part of the DWI process. Phase 1 and Phase 2 also contributed to the final accuracy. So the final accuracy comes from all 3 phases of the DWI process. That's what this video is about. It turns out there are ways to figure out how much of the final accuracy comes from the final step of the process, Phase 3, the sobriety test, and how much comes from the first 2 phases. Not only will you learn the theory about how it's done, we'll actually do it. And you'll see that most of the accuracy of police officers' opinions comes from phases 1 and 2. And that shouldn't be a surprise, because it turns out police officers who ask people how much have you had to drink are pretty good at spotting people who've had something to drink. Just a small and insignificant part of DUI officers' arrest accuracy comes from the sobriety test itself, from the SFST. Scientifically, the SFST is a very weak test. Presenting it as a strong
wrong test, a 91% accurate test, misleads juries and judges.
Traffic police believe their sobriety tests have a property they call accuracy. They give their test to a driver, she fails. The test says her alcohol is high, but no test is perfect. Sometimes this test's answers are correct, sometimes they're wrong. The percent chance an answer is correct is given by a number that traffic police call the accuracy of the test. This is how traffic police understand the mathematics of conditional probability in diagnostic testing.
But the SFST was just the last phase of a complicated DWI process. First, the officer observed the flow of traffic looking for driving that suggested an impaired driver. Then he went to the window and talked to the driver looking for signs of alcohol use. He asked, "How much have you had to drink?" and she answered. In real life, this may be all the officer needs to pick out drunk drivers. A lady driving on the wrong side of the road who admits to 5 doubles and reeks of booze is drunk. You don't need no fancy test. So how should we think about this? Well, suppose the officer didn't administer the SFST. Suppose he just did phases 1 and 2 and stopped. Some drivers would pass phases 1 and 2 and they'd be released without alcohol testing. Others would fail. These drivers would have their alcohol tested. Some would be high, some would be low. The percent of drivers who failed phases 1 and 2 and who also had a high BAC, let's think of that as the accuracy of phases 1 and 2. The SFST hasn't been done yet. It contributes nothing to these evaluations. It contributes nothing to this accuracy. And now suppose that finally the officer takes the driver on to phase 3 of the DWI process. He gives her the traffic police standardized field sobriety test. She fails. The test says her BAC is high. But no test is perfect, including the SFST, so it's still not certain that the driver's BAC is high, but the percent chance did increase some. In fact, we know where it increased to. It ended up at the same 91% that the traffic police talk about. So we've gone the long way around and ended up back at the same spot. But now we see that the contribution of the sobriety test, the scientific accuracy of the SFST, is given not by the final orange accuracy, but just by the final step, the change in percent between the end of phases 1 and 2 and the end of phase 3. In this picture, that's the maroon arrow. So that's it. That's the math in pictures. Pretty easy. And I'm wondering if maybe all this strikes you as fussy and unhelpful. So let's apply what you've learned. Let's do a couple examples. Same diagram, but this time with a real validation study. These are the results of the Los Angeles DRE validation study. NHTSA's 2023 DRE training manual identifies this study as validating the DRE testimony and drug influence evaluations you confront in your practice now. LAPD patrol officers, not DRE officers, patrol officers, identified drivers they thought were maybe impaired by drugs. No DRE testing had yet been done. Those officers arrested some drivers and took them to the station for DREs to do the drug influence evaluations. The subject of this study is the accuracy of those DRE evaluations, the ones down at the station. 94% of the arrested drivers had drugs in their system. These drivers had not yet been seen by a DRE. The traffic police drug influence evaluation contributed nothing to this 94% accuracy. So the driver went down to the station, and that's where a trained and experienced DRE did a complete drug influence evaluation. The DREs considered the totality of these evaluations and formed their expert scientific opinions about driver impairment. And finally, the driver's blood was tested for drugs, blood or urine. How did the opinions compare to the toxicology? When DRE experts formed the opinion that drivers were impaired by drugs, drugs were found in the blood 94% of the time. The DRE's evaluation contributed nothing to the final accuracy of these drivers' assessments. 0%. A coin toss would have been just as accurate. We'll return to this study later in the course. Same diagram, this time another real validation study. Up in the corner are the HTN results of the San Diego SFST validation study. The 2023 SFST training manual identifies this as the latest study to describe SFST accuracy. It teaches officers to bring up this study in court whenever possible. HTN, officers are taught to testify, is the most accurate of all the standardized field sobriety tests. San Diego officers on regular DUI patrol evaluated drivers with phases 1 and 2 of the DWI process. Drivers who passed were released without BAC testing. Drivers who failed phases 1 and 2 were detained. Now, suppose officers had stopped their evaluations at the end of phase 2. Suppose they just arrested all the drivers who failed phases 1 and 2. 72% of those drivers would have had a high BAC. In traffic police terms, the accuracy of phases 1 and 2 was 72%. At this point, no SFSTs had been done. The HTN and the rest of the SFST contributed nothing to this 72%, but the San Diego officers didn't stop. They took the drivers who failed phases 1 and 2 on to phase 3, where they administered the traffic police SFST. We'll look at the HTN results now and the others later in the course. Some drivers passed the HTN test, some failed. No test is perfect, including HTN. If the officers had arrested all the drivers who failed the HTN test, then 87% of the people arrested would have had a high BAC. Traffic police think that means their HTN test is 87% accurate, but it's not. Of that final 87%, most of it came from stuff like asking drivers how much have you had to drink. Only 15% came from the HTN test results. The HTN test isn't 80% accurate. It is, in this study, call it 15% accurate. In fact, we'll see later in the course that the SFST in the San Diego study was so inaccurate that the officers doing the study didn't trust it. The officers doing the study knew as they were doing it that the test was giving answers that were wrong, and they changed and corrected its mistakes. Good. Now that you understand this, we can move on to the hard part of this video. Imagine that you yourself have invented a test that identifies impairment. I want to use your test. No test is perfect. When I do use your test, some of the results will be correct, but others will be wrong. I want to know how often each of those happens. I need to know how much to trust its results. When the test says someone is impaired, what % of the time is that answer correct? I need you to describe your test in a way that lets me answer my question. That's what this video is about. When there's a test that identifies the presence or absence of a condition, how can we describe that test in a way that reveals the % chance that a particular test result is correct? We're going to use sobriety tests as examples, but our real subject is not sobriety tests. Our subject is the science of test accuracy. At the end, I want you to understand how do you describe a test, any test, in a way that communicates what % of the time the test's answers are correct. Before we get to that, let's prepare our brains with a couple of sides. First, and this is hard for attorneys to accept, we are asking about a concrete scientific fact, a physical fact that can be measured and described with numbers. In other circumstances, you might need to know how fast is the car. Speed is a property that can be measured and described with a number. For a sobriety test, the relationship between the test result and the presence of the target condition, between, say, HTN clue counts and impairment, that relationship is an objective property that can be measured and described with numbers. That means that when a driver has an HTN test done, we don't have to guess or estimate or form an expert opinion about what that clue count means. We can go to the scientific studies and look it up. Or we can learn that the cited studies all fail to measure the relationship, and we're dealing with traffic police phrenology. Either the relationship between HTN and impairment has been studied and quantified, or police use of the test is modern phrenology. Second aside, about our how do you describe a test question, you'd think the answer would be accuracy. The accuracy of the test is, but that's not the answer. It's true accuracy is a common word, and in day-to-day conversation, it's a fine way to describe a test. But when scientists get a hold of the common sense word accuracy and turn it into a technical scientific term, a term of art, things get complicated. Science textbooks end up with diagrams like this. I'm not going to inflict that on you, but let's talk about using common words as technical terms. The word size is another common word. It's a fine way in day-to-day conversation to describe how big something is. But when it's used as a technical term, things get complicated. What's the number that describes the size of this box? There's length size, width size, height, surface area, volume. There's a number of pixels in this 2D projection on your screen. Each of those meanings is different, and they each make perfect sense as a technical definition of the size of a box. But that only works as long as you pick one and stick with it and don't mix them up. In this course, layman's accuracy refers to technical accuracy as traffic police misunderstand it. The term comes from traffic police themselves, whose goal is to understand the subject as well as people with no training at all. It doesn't necessarily refer to a specific technical statistic because traffic police don't understand the subject well enough to pick one and stick with it. Scientific accuracy is how this course refers to the technical methods used by real scientists who do know how to describe a test in a way that communicates what % of the time the test's answers are correct. In this course and in real life, the word accuracy is often used in a loose, technical-ish sense to mean the % of the time a test's answers are correct in a particular circumstance. In a few minutes, you're going to understand why that meaning is different from scientific accuracy. And here's a bonus feature of using general words as technical terms of art. Suppose the fine people at Whitley's are using this box to send you peanuts. What size box did you order, a 5-pound box or a 10-pound box? Notice that the size of a box depends on the common sense size of the box, length, width, height, but it also depends on something other than just the box itself. It depends on how heavy the peanuts are. So it's possible for the technical size of the box to depend on stuff other than just the box itself. Test accuracy works the same way. The accuracy of a traffic police sobriety test, the number that describes how often the test's answers are correct, that number depends on the test itself and on other stuff, which means the accuracy of the test is not a useful way to answer our question about the probability the driver was impaired. By the end of this video, you're going to understand why that's true and how to use that scientific fact in your DUI defense practice. In science, the word accuracy is also used to describe the measurement of a physical property. How close is the measured number to the true physical value? Traffic speed guns send out a laser beam and measure the wavelength of laser light reflected off a car. Here the wavelength was measured as 100 plus or minus 5. The speed gun measured this physical property to an accuracy of plus or minus 5. The plus or minus accuracy of the measurement of a physical property is not the subject of this video. It will come up later, and when it does, it will matter to your DUI defense. For example, what is the plus or minus accuracy with which traffic police measure eye angles during their HGN test? The word accuracy could be used to describe the opinions of experts. ER doctors form diagnostic opinions that are either correct or not correct. You could calculate the % of the time these opinions are correct and call that the accuracy of the doctor's opinions. Traffic police do that. They imagine themselves to be trained, experienced scientific experts who consider the totality of a DUI evaluation and form a helpful opinion about the driver's medical condition. And then, because they don't know what they don't know, they calculate what they think is the accuracy of those opinions. And because they think those accuracy numbers validate their opinions, they track them and put them in their annual reports and take them to court and use them to put people in prison. This is bad science. Later in this course, you'll learn to turn it to your advantage. For now, the accuracy of expert opinions is not the subject of this video. How about the question we want to use at trial? The lady took a traffic police sobriety test and failed. What is the % chance she has a high BAC? Let's be clear about what we're asking. We all have some normal baseline mental and physical state. Alcohol changes that. Traffic police have convinced themselves they can identify alcohol changes by measuring certain physical properties. They measure eye movements and angles, and those measurements have some plus or minus accuracy, something like 45 plus or minus 20 degrees. That's not the meaning of accuracy that we're considering here. Police claim to use a driver's eye measurements and coordination scores to predict the presence or absence of a high BAC. It makes good common sense to describe those predictions as accurate or not. What you'll learn in this video is that that doesn't work. The vocabulary is wrong because the concept is wrong. I want you to learn what does work and how to use that science in your DUI defense practice. Okay, we're back. Remember, you invented a test. I want to use your test. How can you describe a test, any test, in a way that communicates what % of the time the test's answers are correct? Traffic police answer that question. They just use common sense. Tests have a property called accuracy, and that property describes how often the test answers are correct. In this picture, the officer administers a sobriety test. The driver fails. The test says she is impaired. Maybe she is, maybe she isn't. No test is perfect. The percent chance that this result is correct, that she's impaired, is given by the accuracy of the test. In the picture, that puts her on the scale between 0% and 100%, right at the point accuracy percent. The SFST training manual describes this as a layman level of understanding. Yes, it is. So what do scientists do? I'll jump to the final answer and we'll fill in details as we go along. This is stuff traffic police don't know they don't know. In real science, tests that identify the presence or absence of a condition, for short they're called diagnostic tests, are described with two numbers. The names are here. These are the properties of a diagnostic test that quantify its ability to tell the difference between people who do and do not have the condition tested for, the target condition. At this point, don't worry about details. I just want you to know that there are two numbers. So when you tell me you have invented a new sobriety test, and I ask you to describe the test in a way that will let me figure out what percent of the test answers are correct, you will give me two numbers: the sensitivity and specificity of the test. But accuracy is hard, and now things get tricky. Even after you give me those two numbers, I still can't calculate the percent chance the test's answers are correct. I need more. I need a number describing the circumstances in which the test was given. There are several names for this. In this video, the number will always be yellow. For now, all I want you to know is that the diagnostic performance of a diagnostic test is described with two numbers, and calculating the percent chance a test result is correct needs one more number for a total of 3. Accuracy is hard. By the way, we're not surprised that something has a property that it takes more than one number to describe. Describing a shipping box takes 3 numbers, and you can think up other examples of your own. Without the math, once you see how it works, accuracy is pretty easy. Guy throws a fishing net. How many fish does he catch? The answer depends on properties of the net. What size is it? How big is the mesh? Okay, 10-foot net, 1-inch mesh. Now, how many fish does the guy catch? You still don't know. How many fish a net catches depends not just on the net, but also on how many fish are in that water in that place at that time. How many fish a net catches depends on properties of the net and on the circumstances in which that particular throw happened. Depending on the state of the water, the number of fish there, and then maybe the net caught 0 fish, maybe it caught hundreds. Now, suppose I tell you the sensitivity and specificity of a sobriety test and that the officer administered the test to a driver. She failed. Question: what's the percent chance she had a high BAC? Answer: you don't know. The answer could be 0% or 100% or any number in between. The probability that a driver who failed the SFST has a high BAC depends on the properties of the test and on the percentage of drivers on that road at that time who were impaired. Good. If you understand this picture, you have a good intuitive understanding of how accuracy works. Now for a bonus. Traffic police say their SFST is 91% accurate and their DRE testing is 94% accurate. Those numbers come from the validation studies. Using those numbers is equivalent to saying this fishing net always catches 94 fish anytime, anywhere it's thrown. So where do those high numbers come from? Well, one way to be sure your net always catches a lot of fish is to do your fish net validation study in a stocked pond. They've got places like that around here where I live. The business has a private lake, and they keep it absolutely full of fish. You take your little kids there, and they can't not catch a fish. NHTSA's validation studies work the same way. They stock the sobriety test pond with drunks. They pre-select a bunch of people who are obviously drunk or impaired, and then, after they've identified those folks, then the officer experts come in and look for clues and indicators. They can't not find impaired people. In the main drug study, Compton's Los Angeles DRE study, officers were 94% accurate. But in that same study, if they had just flipped a coin, heads drugs, tails no drugs, they would still have been 94% accurate. And you can find this calculation in the 2013 study linked in the description below. SFSTs and DREs appear accurate because they're validated in a stocked pond. But let's not get off track. If you understand this picture, you have a good intuitive understanding of how accuracy works. Now the tricky bit. Converting our easy intuition into numbers turns out to be surprisingly complicated and counterintuitive. Accuracy math is hard. Traffic police teach each other to understand accuracy at what they call a layman's level. They tell each other that accuracy is a number, one number. It's like the accuracy of a bow and arrow, describing how many inches the arrow is from the center. You can even print circles on the target showing different degrees of one number accuracy. For any particular arrow shot, you can measure the distance to the center and quantify its accuracy with one number. This is good common sense layman's accuracy. The trouble is the one number theory doesn't work. Traffic police can't keep their story straight. Let me show you what I mean. Here's a page from the manual traffic police use to teach each other how to do their sobriety testing. So how accurate is HGN? Simple. 88%. HGN is 88% accurate. Simple. Easy. And that's all you got to know to interpret an HGN test. This is the number traffic police bring to court. This is the number prosecutors use to put people in prison. But let's go behind the courtroom testimony and look at the official canonical validation studies. As soon as NHTSA's validation contractors have to describe their data, the layman's one number theory fails. Here's NHTSA's Colorado validation study trying to describe the performance of officers using the SFST. The contractor is unable to quantify the officer's performance with one number. The study ends up giving three numbers. Each of these accuracies answers a different question about the Colorado test. How often was the test correct when the driver failed? Orange, 93%. How often was the test correct when the driver passed? In green, 64%. How often was the test correct when you consider all the answers altogether? Pink, 86%. It's the same for NHTSA's Florida validation study, where the contractor cannot give a single accuracy number, one number, that describes the performance of the SFST. How often was the test correct when the driver failed? Orange, 95. How often was the test correct when the driver passed? Green, 82. Here's NHTSA's San Diego validation study describing the performance of HGN. Three numbers, three different accuracies. NHTSA's training manuals tell officers that sobriety tests have one accuracy. NHTSA's validation studies say otherwise. To understand what's going on, let's think about the goal of testing. There's a thing. We want to know some of its properties. What are the dimensions of the box? We measure directly. But some properties are inconvenient to measure directly, so we measure something else and convert. That's a plot line. Some properties are inconvenient to measure directly, so we measure something else and convert. A radar speed gun works like that. What we care about is the speed of the car. What the speed gun actually measures is the wavelength of the laser light reflected off the car. And some smart person came up with a scientific theory, a formula, to convert that measured wavelength into what we care about, the speed of the car. So the officer uses the speed gun to measure the wavelength of reflected light, and inside the speed gun, special cogs and wheels use that clever formula to convert the wavelength into the speed of the car. And the result, the speed, the calculated speed, is given as evidence at trial. Notice that in this setup, in its use at trial, the speed of the car is never actually measured. The only thing that is physically measured is the wavelength of the reflected light. But you know, sneaky defense lawyers aren't going to let this go in unchallenged. At some point, there must have been a speed gun validation study to compare the theoretical wavelength predictions with the actual measured speed of the car. So how would you do that study? Well, you would measure one thing, you'd measure two. In effect, you'd measure the speed twice and compare. You'd have the car drive by the speed gun and you'd write down the predicted speed, thing number one. At the same time, the driver would look at the speedometer and write that down, thing number two. You do this over and over and write down the results each time, number one and number two. And you'd end up with a long list of results, thing number one matched with thing number two over and over. The question would be, if I know thing number one, how accurately can I predict thing number two? For the speed gun, presumably the study found that thing number one accurately predicted thing number two, and there was an evidentiary hearing and a ruling, and now case law says the results of a properly maintained and calibrated speed gun are admissible as evidence of speeding. That sequence, that method of validating a test, will be helpful to us in upcoming videos. For now, let's think about using thing number 1 to predict thing number 2. How do we describe this process in a way that communicates what % of the time the predictions are correct? Let's have an example. SFSTs. Police officers measure physical properties of the driver, eye movements, balance, coordination, thing number 1. Traffic police have convinced attorneys they can use thing number 1 to predict thing number 2. They're fluid about what thing number 2 is, impairment sometimes, other times BAC or toxicology or driving abilities, something like that. More about this later in the course. For now, we'll just follow the validation studies and say BAC. That makes the SFST like the speed gun. It's one of those don't care types of tests. It's not illegal to have a neuro-ophthalmologic exam done by a traffic policeman who thinks he sees abnormal eye movements that he thinks are nystagmus. It's not illegal to be unable to walk an invisible Olympic balance beam or to perch on one leg with less than perfect coordination. The law doesn't care about thing number 1. It does care about thing number 2. It's illegal to drive while your mental or physical condition is impaired by alcohol or drugs. Traffic police do a physical exam in which they measure some physical properties, thing number 1. Then they supposedly use thing number 1 to predict thing number 2, BAC. Science question. How can we describe the degree to which thing number 1 predicts thing number 2? Let's use one of NHTSA's own canonical validation studies. This is the first SFST study printed back in 1977. Remember, our point here is not the actual scientific accuracy of the sobriety test. The testing here was early and unstandardized. It's not what's done today. We don't care what the accuracy was. What we do care about is you learning how to describe the predictive power of a test where thing number 1 predicts thing number 2. Remember how I said accuracy was hard? Yeah, now we're at that part. These are results of this validation study copied and pasted from the original. Here's how it worked. The contractor got together a group of people to be subjects of the study. Some people were given alcohol, others were not. Each person had 2 tests done, a sobriety test and a blood test for alcohol. The contractor had officers administer a rudimentary sobriety test, after which the officer decided whether or not he would arrest the person. That's thing number 1, officer's decisions. Then each driver also had their blood alcohol measure. That's thing number 2, BAC. The contractor counted up results and put them in this table. The stuff around the edges we should ignore for now. The labels in the middle can be confusing because the contractor used terms like hit and correct rejection rather than the structured terminology you're probably familiar with, true positive, false negative, and so on. I've added the familiar terms in red, but even that's too much at this point. These are the raw results of how this sobriety test worked. This is how thing number 1 predicted thing number 2. Each subject person had 2 tests done, and based on the results, each person was tallied in one of these 4 boxes. People who the officer decided to arrest and who also had a high BAC went in the box at the top left, 54 of those, and so on. Every person was counted one time in one of these boxes. And by the way, when NHTSA paid for this study, they didn't click on the proofreading package. The contractor mislabeled this table, and I've corrected it here. All right, these are the results of the scientific validation study. The government paid multiple tens of thousands of dollars to get these 4 numbers. But how do we describe them? Well, let's start by noticing that 2 of the boxes count up answers that are correct, true positive and true negative answers. Here they are. How often did that happen? Let's calculate percentages. The study report helps us to do that by adding up the rows and the columns. Row 1, 54 plus 10 equals 64. Column 1, 54 plus 47 equals 101, and so on. Down in the corner in red is the count of all the people tested. 54 plus 10 plus 47 plus 127 is equal to 238. 238 subjects in the study. Now we can calculate percentages and notice the headings. Percent correct. On the right, the red and the blue numbers report what percent of the times the results in each row were correct. Look at the top row in red. When the sobriety test was given to people who actually had a high BAC, the test answers were correct. 54 divided by 64 equals 84% of the time. When it was given to people with a high BAC, the test was 84% accurate. Look at the first column in orange. When the test said the person had a high BAC, that answer was correct. 54 divided by 101 equals 53% of the time. Hey, wait a minute. How come those numbers are so different? They're both about people with a high BAC. How come one accuracy is pretty good good. 84% is pretty good, but the other is terrible. 53% is basically a coin toss. A coin toss, BAC, high, yes or no, is correct 50% of the time. These numbers both describe how the test dealt with people with a high BAC, but the questions they answer are slightly different. Red 84. When the test is given to people who actually have a high BAC, how often is the answer correct? Orange 53. When the test says the person has a high BAC, how often is the answer correct? Accuracy is hard. A test doesn't have one accuracy, it has at least five. 5 different accuracy numbers, each answering a different question about the test. Here they are in color. Each accuracy number answers a different question about the test's performance. They have scientific names which are hard to keep straight at first, so we'll mainly just use colors. The colors in the bottom row, you saw those earlier. These are the accuracies reported in NHTSA's validation studies. Each question begins with a setup clause and finishes with how often is the answer correct. The setup just repeats the heading of the row or the column. Green, when the officer's decision is don't arrest, how often is the answer correct? 127 divided by 137 equals 93%. Blue, when the test is given to drivers whose BAC is below 0.10, how often is the answer correct? 127 divided by 174 is 73%. This pink answer is the overall accuracy. It answers the question of all the tests done, how often was the answer correct? 54 plus 127 divided by 238 equals 76%. You saw this accuracy earlier. This is the accuracy NHTSA puts in the SFST training manual. Officers are told that the HGN test is 88% accurate. That's the pink overall accuracy. But look at the manual. This is the heading for the orange column. Traffic police use the pink accuracy to answer the orange question. What they teach each other is wrong. What they testify to in court is wrong. When traffic police follow their training, they mislead the judge and jury. Traffic police don't know what they don't know. Accuracy is hard. Accuracy is hard. Tests don't have one accuracy, they have 5. The temptation is to be a little loose and just use the pink overall accuracy to answer every question. But look what happens. 76 is different from 84 and way different from 53 and 93. In this study, whatever other question you're asking, the pink accuracy is always wrong. All right. Accuracy is hard, but it's not that hard. The obvious fix is to just pick the question you care about and use that accuracy. And that's what NHTSA's contractor did in this study. She calculated that when officers used this sobriety test to decide whether to arrest someone, their answers were correct only 53% of the time, and she thought that meant her new sobriety test didn't work. She was wrong. I mean, she was right that the test didn't work, but the reason she was right was wrong. Anyway, she was wrong. She didn't know what she didn't know. She failed to consider a control group. The nation is gripped by an epidemic of pneumonia. People are dying. Can penicillin help? Scientists do a penicillin validation study. They find people with pneumonia and give them penicillin. They count how many survive. 80% survive. Question: when pneumonia patients are given penicillin, how many survive? Answer: 80%. Penicillin is 80% effective at curing pneumonia. Excellent. Somebody says, maybe we should include a control group. Scientists do another validation study. Some people with pneumonia, they give penicillin, 80% survive. Some people with pneumonia, they give a sugar pill, 75% survive. Question: how do we describe the effectiveness of penicillin at treating pneumonia? Without penicillin, 75% survive. With penicillin, 80% do. That's a difference of 5%. The effect of penicillin is not to make 80% of people survive. The effect is to increase their survival by 5%. 5% is way different from 80%. Control groups are important. Here's an HGN validation study with and without a control group. How will we describe the effectiveness of HGN? Police stop and evaluate a group of drivers. In this study, officers give drivers an HGN test and they arrest everybody who fails. Back at the station, they also do a BAC test. They discover that when people fail the HGN test, 87% have a high BAC. The orange accuracy of the HGN test, the arrest accuracy, is 87%. Somebody says, maybe we should do it again with the control group. Scientists do another study. They split the drivers into 2 groups. One group, they give an HGN test. People who fail are arrested. As before, when people fail the HGN test, 87% have a high BAC. The orange accuracy of the HGN test, the arrest accuracy, is 87%. Pretty good. The other people, they don't do the HGN test. Police just arrest everybody. Back at the station, these folks each also get a BAC test. Some percentage of these people have a high BAC. We'll pick a number. Let's say 72%. Without HGN, 72%. With HGN, 87%. The effect of HGN was to increase the percentage of arrests that were correct from 72 to 87. HGN did not create 87% accuracy. It changed the accuracy by 15%. 15% is way different from 87. Control groups are important. The good news is, and this is not obvious, that for sobriety tests, scientists can include a control group without doing a second validation study. The data they need to calculate the control group accuracy is already included in the validation study's table of results. You just have to know how to read those results. Here are the results for NHTSA's 1977 sobriety test validation study. And remember, our purpose here is not to discover the actual accuracy of this outdated test. Our purpose is for you to learn how scientific accuracy works. The sobriety test was given to 238 people. Of those 238 people, 64 had a high BAC. Neither of these two numbers has anything to do with the sobriety test itself. They just describe how the study was set up. 27% of the people in this study had a high BAC. In this canonical validation study, if officers had skipped doing the sobriety test and just arrested every person in the study, the accuracy of those arrests would have been 27%. This sobriety test did not create the orange accuracy of 53%. It changed the yellow control group accuracy into the orange arrest accuracy. It changed 27% into 53%. The sobriety test contributed 26% to the final accuracy. Accuracy is hard. A test doesn't have one accuracy. It has at least 5. The simple fix is to pick the accuracy that answers the question you care about. But tests don't create accuracies, they change them. To describe the diagnostic performance of a test, you have to include a control group and calculate the contribution of the test to the final accuracy. All right, good for us. Accuracy is hard, but we figured it out. The diagnostic performance of a test is described not by its orange accuracy, but by its maroon arrow contribution to the orange accuracy, by the degree to which the test changes control group accuracy. By the way, heads up, this yellow accuracy number is a big deal. It goes by different technical names. Scientists call the yellow number prevalence when they're talking about the group of people who are being given the test. Prevalence is the percent of people in the group being tested who have the target condition. At a DUI checkpoint, prevalence is the percent of drivers on this road tonight who have a high BAC. Scientists also call the same yellow number the pretest probability. They do that when they're talking about one person. It's really a statement about what you know about the person who's about to get the test. Given what you know about them, the probability they have the target condition is the pretest probability. Once they have finished the test, you know more about them, you know their test result. Knowing that result will let you determine the orange post-test probability that they have the target condition. At a DUI checkpoint, pretest probability is the percent chance that this particular driver, the one the officer is evaluating now, has a high BAC. Control group accuracy is a term I made up for this video. If you want to be highfalutin, we should call the yellow control group accuracy the control group prevalence. Don't let this confuse you. In fact, prevalence and pretest probability and yellow control group accuracy are all the same thing. They're all the same number. Anyway, back to the story. We have solved the accuracy problem. The way to describe this 1977 sobriety test is to say this test increases the probability of a high BAC by 26%. Or does it? Accuracy is hard. Let me draw your attention to the yellow pretest probability. Also, keep in mind the red and the blue accuracies, and now make sure you're sitting down because I'm going to show you something amazing. This is a table from a famous scientific study, Dr. Vecchio's paper in the New England Journal of Medicine back in the 1960s. The paper explains the basic mathematics of accuracy science. This is stuff traffic police don't know, they don't know. The math in this paper is hard, but the takeaway result is easy, and wait a few minutes and I'll give you some pictures. The title up in the corner tells us what the paper is about. Predictive value is the technical term for the orange arrest accuracy. What is the orange arrest accuracy of a test? Unselected population is about the yellow accuracy. Unselected means we're going to give the test to people who maybe have the target condition or maybe they don't. When we administer the test, the prevalence of the condition is not known to us. Each time we give someone the test, their yellow pretest probability may be high or may be low. This paper isn't about how to do the calculations. In 1966, that was already old science. What the paper does is remind doctors about the surprising and counterintuitive and clinically essential results of those calculations. Did you catch that plot line? You didn't know, you didn't expect it, and it matters a lot. Dr. V chose as his example a hypothetical test that was highly accurate. Remember the red and the blue accuracies from our sobriety test table? For Dr. Vecchio's illustrative example, for his test, each of those accuracies was 95%. When this test is given to people with the target condition, it gives the correct answer 95% of the time. When this test is given to people without the target condition, it gives the correct answer 95% of the time. So of our 5 questions about a test, that's 2 of them already answered. Now Dr. V asks a third question. For this test, what's the orange accuracy? When people fail this test, what is the probability the test's answer is correct? You know about control groups and about their yellow probabilities. You know that a test adds a maroon arrow contribution to the yellow pretest probability. Dr. V knew that too, so he did his calculation over and over for various yellow percentages. Since he was thinking in terms of groups, he called the yellow number disease prevalence. And for each different yellow percent, he calculated the orange accuracy, only he used the technical term positive predictive value. Nowadays, we do calculations like this on a computer. People in 1966 were very primitive. They did these calculations by rubbing 2 sticks together. So here are Dr. V's results. We have a test whose scientific accuracies are 95 and 95, and we administer that test and we ask the question, when somebody fails this test, what is the probability they have the target condition? And the answer is only 16%. The scientific accuracies of this test are 95 and 95, and when the test says somebody has the target condition, that answer is wrong 84% of the time. Did you see that coming? Because most people don't. The maroon arrow contribution of this highly accurate test is only 15%, also unexpected. It gets more unexpecteder. When the yellow percent changes, so does the maroon contribution of the test. The implications of a test change depending on who the test is given to. Okay, so here's a setup. A lady took Dr. V's highly accurate test. Her test result was positive. It says she has the target condition. Question: what's the percent chance she has the target condition? Look at the table. Is it 16% or is it 67% or 98%? Which number do you use? And tell me why you chose that one. Your task is to describe what laymen call the accuracy of a test. Accuracy is hard. There's not one accuracy, there are 5. Each one answers a different question about the test. Fine, we'll pick the one that answers the question we care about. Nope, you got to consider the control group and calculate the maroon contribution. But that doesn't work because the contribution changes every time the control group changes. What laymen call the accuracy of a test, that number changes depending on where and when the test is given. When exactly the same officers do exactly the same test, which they interpret in exactly the same way, the number that traffic police use to describe the test, the layman's accuracy, can be 0% or 100% or any number in between, depending on where and when the test was given. Accuracy is hard. Setup. A lady has a casting net that is 10 feet across with a 1-inch mesh. She throws the net. Question: does she catch 16 fish or 67 or 98 or some other number? The answer is the number of fish a net catches depends on the properties of the net and on the number of fish available to be caught. Dr. V's scientific journal article quantifies that intuition. At this point, scientists stop. They don't really give up. They just recognize that it can't be done. You cannot consider a test in isolation and give an orange number that represents the percent of the time the answers are correct. The need for a control group makes that impossible. Scientists do describe the strength of diagnostic tests. They quantify the diagnostic performance of tests with the red and blue accuracies. Those 2 numbers don't change as the yellow prevalence changes. They are properties of the test, just like the diameter diameter and mesh size are unchanging properties of the fishnet. These scientific accuracies have names. Red is sensitivity, blue, specificity. When scientists describe a test, they quantify its diagnostic performance with two numbers, sensitivity and specificity. You need to know that fact, and you need to know those names. So that's it for now. But because we're here, I'll mention one other feature of test accuracy that will come up later in the course. The sensitivity of a test, the red accuracy, doesn't vary as the prevalence changes, but it does vary as the severity of the condition tested for changes. There are different levels of drunk. Sloppy drunk is easier to spot than a little bit tipsy. The accuracy of a sobriety test at identifying sloppy drunk is higher than the accuracy of the same test at identifying just a little bit tipsy. When he explains this to the judge, your expert will use the science words spectrum bias. More about this later in the course. I realize if you're hearing this for the first time, it's gotta sound arcane and theoretical, and why should you care? It turns out this weird feature of test accuracy is one of those obscure technical things that people like doctors who interpret diagnostic tests for a living know and use every day. I haven't done a formal survey, but this math is in every textbook of medicine I know about, generally with a chapter of its own up towards the front. This book here is an example. This is Dr. Sitek. If you're in the business, you know who he is. He's an accomplished, intelligent, articulate optometrist who flies in a lot to testify about sobriety testing. His paper record, his CV and transcripts tie him to relying on this 1988 edition of Cecil's Textbook of Medicine, which has a chapter explaining the same control group stuff you've been learning about here, the same prevalence dependence science in Dr. V's article. And since we're here as a warning, notice that Cecil's teaches a version of this math called Bayes' theorem, and being Cecil's, it does that badly. Your warning is you're going to come across articles that teach how to describe tests by using Bayes' theorem. Keep away from them. They are about probability theory. They use a dense technical notation that's just not accessible to laymen. Bayes' theorem has a handy medical version. In fact, we use it in our paper about SFST accuracy, Kane 2021, which is linked below, but it's messy and you don't need it. Avoid Bayes' theorem. Anyway, to bring home the point about prevalence dependence, Dr. Sitek's oft-cited Cecil's has its own version of Dr. V's unexpected results. Here, a person took a cancer screening test. The test said, yes, he has cancer, and the orange post-test probability that he actually did have cancer was only 4%. You didn't expect this prevalence dependent surprise, but it turns out to be a standard chapter in all the standard textbooks, a key feature of diagnostic tests like the SFST. By the way, these pages of Dr. Sitek's go-to texts are all marked up. We were prepping to cross him with them so the attorney could lead him to admitting Dr. V's prevalence surprise and its wipeout of NHTSA's arrest accuracy statistic. In the event, he gave up the point on his own before the hearing, which seemed to us like an unforced error because it sort of forces him to testify, as I paraphrase. Yeah, sober people who take the SFST are wrongly identified as impaired, but that's not a problem because police only administer the test to guilty people. If you have occasion to cross Dr. Sitek, you're going to want to get a copy of his testimony in New Jersey's Olenowski hearing. Now the pictures. NHTSA's sobriety test training manuals and validation studies and traffic police officers all have what they call a layman level understanding of the mathematics of conditional probability and diagnostic testing. They don't know what they don't know. They believe that diagnostic tests have a property they call accuracy. They administer the test, the driver fails. The accuracy of the test quantifies the percent chance the driver's BAC is high. Anytime, anywhere the test is used, its accuracy is always the same. This is the I tested it in a stocked pond and my net always catches 94 fish theory of diagnostic testing. Real accuracy is harder than that. Police use various methods to select the drivers who they think may have a high BAC. After they've been selected, then these drivers go on to have an SFST done. Some of the selected drivers will have a high BAC and some won't. The highfalutin way to say this is the group of drivers selected has some prevalence of high BAC. No sobriety testing has been done yet. After the selection process, officers do their sobriety test. When a driver fails, the probability her BAC is high increases from the yellow prevalence number by the maroon arrow amount to the orange number. Traffic police call this number the arrest accuracy. Scientists call it the positive predictive value, or same thing, the post-test probability of a high BAC. When the prevalence goes up, the orange accuracy goes up. This is a cause and effect relationship. The cause of the higher orange accuracy is the higher prevalence. When the number of fish in the water goes up, the number of fishing net catches goes up. When the prevalence goes down, the orange accuracy goes down. When the number of fish in the water goes down, the number of fishing net catches goes down. So the final orange accuracy has two causes, the yellow prevalence and the maroon arrow. The yellow prevalence has its own cause, whatever method officers use to pick drivers to test. This is prior to and unrelated to the SFST. The strength of the maroon arrow reflects the strength of the SFST itself. For weak tests like the SFST, the maroon arrow is always short, and the orange accuracy basically just follows the orange prevalence up and down the scale. Let's do some real SFST science. Up in the corner, I've copied and pasted the HGN accuracy table from NHTSA's canonical San Diego SFST validation study. Traffic police misuse of this table puts people in prison. This table works just like the colorful one we've been using. The orange accuracy, the arrest accuracy of the HGN was 87%. In this study, real traffic police administered their HGN test to real drivers in real DUI investigations. If officers had arrested just those drivers who failed the traffic police HGN test, then 87% of those drivers would have had a high BAC. Traffic police are taught to testify that this means the HGN is 87% accurate. You know better. You know about control groups. You know how to look at this table and calculate that the orange control group accuracy was 72%. You know scientists call this number the prevalence or pretest probability. You know how to look at this table and determine that the maroon arrow contribution of HGN was 87 minus 72 equals 15%. HGN was not 87% accurate, it was 15% accurate. It will help judges and juries to know that. But you're not done. This contingency table, traffic police call it a decision matrix, doesn't just tell us about the traffic police HGN test, it also tells us how the validation study itself was done. Officers, usually working the night shift in the bar district, observed the flow of traffic and chose some cars to pull over. They went up to the window and talked to the driver. They asked, "How much have you had to drink?" They looked for obvious signs of drunkenness. This part of the DUI evaluation, watching for bad driving and talking to the driver at the window, traffic police call this phase 1 and phase 2 of their evaluation. In this study, people who passed phases 1 and 2 were released without an SFST. Their evaluations are not reported in the study's results. They are not counted in this table. People who failed phases 1 and 2 went on to phase 3. That's the part with the SFST. In other words, this validation study had officers pre-screen drivers to identify people who are probably drunk, and only then did they administer the SFST. This table tells us the results. 72% of the drivers identified by pre-screening actually had a high BAC. No SFSTs had been done yet. The SFST contributed nothing to this accuracy. Then officers administered the HGN test. Of the pre-screened people who went on to fail the traffic police HGN test, 87% had a high BAC. The traffic police don't know what they don't know. They think this means that their HGN test is 87% accurate. Traffic police tell judges and juries this means the traffic police HGN test is 87% accurate. You learned in part 1 of this series that in court the presentation of traffic police sobriety testing is a magic trick. It distorts cause and effect. It misleads people about cause and effect. This orange accuracy is the magic effect part of that trick, the amazing thing that happened. The audience mechanism, the apparent cause, is the HGN test. But HGN was not the cause. This table reveals the real cause, the pre-screening. It turns out police officers who ask drivers how much have you had to drink are pretty good at identifying drivers who have had something to drink, and then they do their HGN test. Notice that officers don't have to identify every drinking driver. They just have to be sure the people they do choose have been drinking, have a high BAC. More about this later in the course. For now, you should understand, and your expert should be able to explain, that this table from the official validation study that officers are trained to cite in court documents the objective scientific fact that the source of HGN's high orange orange accuracy is not the maroon arrow HGN test. It is the yellow phase 1 and phase 2 pre-screening. And this is true not just for HGN, but for each of the 3 SFST subtests. The San Diego study has similar tables for walk-in turn and one-leg stand, and they prove the same thing about those tests. They are weak tests. They look accurate only because of the stocked pond pre-screening. Congratulations. Congratulations on sticking around through the hard part. The fanfare means it's time to put the purpose of this video into one sentence. The orange arrest accuracy and the pink overall accuracy do not quantify the probability that a driver who failed the SFST had a high BAC. Good. Just a few minutes ago you didn't know this science, and now you understand it. Welcome to the light. Now you are one of us. Review. We need to know how much trust to put in a test's results. Our goal is to describe a test in a way that reveals the % chance that a test result is correct. Traffic police think they can do that by telling you one number, which they call accuracy. They believe that number reflects an unchanging property of the test. They are wrong. They don't know what they don't know about control groups. Failing to account for control groups leads traffic police to greatly overstate the power of their sobriety tests. Their sobriety test testimony misleads judges and juries. Scientists quantify the diagnostic performance of a test with 2 numbers, 2 properties of the test itself. There's a third number to consider when the test is administered to someone and it comes time to understand the implications of the results. Scientists know you need a third number, a yellow number, that quantifies the equivalent of how many fish are in that water at that time. And now you know why accuracy is hard. Boy howdy. Remember this from the beginning? At your next impaired driving trial, a traffic policeman will testify that your client failed a traffic police sobriety test that traffic police science says is highly accurate, and the results of that test indicate your client was impaired. Now that you are one of us, let's look at this more closely. You know where this study comes from. The SFST training manual identifies one validation study, the 1998 Stuster and Burns San Diego study, as being the project officers should reference in court as evidence of the accuracy of the SFST. These numbers from that study you saw earlier. San Diego reports these 3 accuracy numbers as describing the performance of the traffic police HGN test, and the SFST training manual uses one of those numbers from that one study as the source of the officer's testimony about the accuracy of the HGN test. At your next trial, if the officer follows his training, his testimony about the accuracy of the defendant's HGN test will come from the San Diego validation study, and the officer's layman misunderstanding of accuracy will lead him to believe that number, that accuracy number, describes the probability that a person who fails the test was impaired, and that's how he'll testify. And because you stuck around through this long and difficult video, now you know that's our modern equivalent of phrenology, amateur science done by earnest people who just don't know what they don't know. But you do know. You know the statistic the officer uses does not describe the sobriety test in a way that communicates what % of the time the test's answers are correct. You know his accuracy number does not quantify the probability that someone who failed the test has the target condition. You know his testimony will wildly overstate the accuracy of your client's sobriety test and will mislead the jury. I'm guessing that if you ever call a sobriety test expert, you'll expect him to understand this basic sobriety test accuracy science. This study, published by Oxford University Press, may help your experts. What Dr. Vecchio did for his highly accurate but hypothetical test, calculate the orange accuracy for each yellow control group percentage, this Kane study does for the SFST. For each yellow control group percentage, Kane calculates the pink overall accuracy and the orange arrest accuracy of real SFST tests done in the field by real DUI officers on real patrol, evaluating real DUI suspects and leading to real prosecutions. The difference is Dr. Vecchio used a hypothetical test. Kane used the actual raw data from exactly the same San Diego study officers learn about in their training. After a bunch of sciencey stuff, Kane comes to this conclusion: the pink overall accuracy and the orange arrest accuracy do not quantify the probability that a driver who failed the SFST had a high BAC or was impaired. The officer's testimony about the meaning and relevance of your client's test results is wrong, scientifically wrong. It is true that NHTSA's validation studies do report high orange accuracy numbers, and the reason they do that is they start with high yellow control group percentages. Kane's science confirms your expert's testimony. Remember that sentence, I suggest you make the sobriety test question at issue in an impaired driving case? Does the fact a driver had HGN make it more likely she was impaired? Kane's Oxford study answers that question. The pink overall accuracy and the orange arrest accuracy do not quantify the probability at issue. The so-called accuracies the officers testify about do not describe how likely it is the defendant was impaired. The officer's testimony is wrong and misleading. And the reason, Kane shows, and there's a simple table you can show juries, is that the pink and orange accuracies are prevalence dependent. They depend on the control group. The science says you got to consider a control group. Police don't do that. So all this stuff you've been learning comes down to one thing that's easy to explain. You got to consider a control group. This officer failed to do that. He failed to follow that simple, basic science. His testimony about this driver's SFST is just wrong. Most folks have heard of control groups, and this is not a hard sell. Here's a pair of terms your expert can use to quickly summarize this stuff in this video. Internally valid and externally valid. There's no new science here, just convenient, concise, scientific vocabulary. Come with me now back to 1977 and that first SFST validation study. Remember these 5 accuracies? Each one correctly describes a feature of the sobriety test in this study. Each of these numbers is internally valid. It correctly describes the test in this study with the control group in this study. The other science term is externally valid. The red accuracy and the blue accuracy in this study are externally valid. They correctly describe the performance of this test in this study and outside the study in situations with other yellow control group percentages. So right now, today, decades after this study, if officers in your town do this same testing, which they interpret in the same way, the red sensitivity and the blue specificity accuracy of those tests will be 84 and 73%, the same as in this old study. These accuracies are properties of the test itself. They don't depend on the control group. These accuracies are externally valid. The orange, green, and pink accuracies are not that way. They are not externally valid. They depend on the test itself and on the yellow control group percentage. When the yellow percentages changes, so do these numbers, even though the test itself stays exactly the same. Even when your client's SFST officer does exactly the same SFST as the one in the San Diego study, which he interprets according to the same standards, the orange arrest accuracy and the pink overall accuracy reported in the San Diego study do not describe the performance of your client's test because those statistics are not externally valid. Externally and internally valid are helpful scientific terms you and your expert can use to explain to juries the relationship between the validation studies and your client's sobriety testing. This study from 2013 explains the difference between internally and externally valid and confirms that orange arrest accuracy is not externally valid. The study also gives an overview of the unexpectedly complicated issues in describing the performance of a diagnostic test like the traffic police sobriety tests. These videos are here to teach attorneys, not to drum up expert witness jobs for me. It's true I am the author of peer-reviewed scientific journal articles about SFST and DRE testing, and I've been repeatedly accepted by courts as an expert in the scientific interpretation of SFST and drug influence evaluation test results. Hooray for me. It's also true I'm retired and I don't need your money, and anyway, you don't have enough of it to induce me to get on a commercial jet and fly around the country. Don't call me to testify. I don't do that anymore. On the other hand, if you're working on an extended Brightful style case, I've done that before, and if you want to chat, my contact info is in the description. Also, when you find stuff in these videos that isn't clear or is wrong, drop me a line. Next time.